University STEM programs lose a massive percentage of their students every year, and the breaking point is almost always foundational math courses. When required calculus or linear algebra proves too difficult, the academic trajectory cracks. Over the last 30 years, an entire research field emerged to solve this exact bottleneck. University Mathematics Education, or UME, was built to diagnose why students fail in lecture halls like these and how professors can fix it. Early research isolated the problem as a cognitive gap. High school mathematics relies heavily on concrete calculation, while university mathematics demands formal, abstract, structural thinking. To understand why students struggle to bridge that gap, math researchers began pulling tools from outside disciplines. They looked to psychology to study motivation and sociology to analyze classroom interaction, but importing outside methods creates a structural identity crisis. Measuring a student's frustration tolerance might yield clean behavioral data, but it risks stripping the actual, rigorous mathematics completely out of the equation. Educational research is currently split between two different camps. On one side, pure mathematical epistemology analyzes the logical structure of theorems. On the other, quantitative behavioral research relies on large-scale psychological surveys. These two domains operate on entirely different assumptions about what knowledge actually is. One treats math as an objective architectural truth, the other treats it as an emotional and cognitive variable. Navigating this conflict requires a theory capable of integrating mathematical logic with human behavior without sacrificing the precision of either. Until we resolve this underlying theoretical tension, our attempts to improve teaching interventions in the lecture hall will continue to fail. The traditional foundation of German math education relies on Stoffdidaktik, subject matter didactics. It focuses purely on the internal, logical structure of the mathematics itself. Its central mechanism is Grundvorstellungen, or foundational intuitions, designed to anchor abstract formalisms to concrete mental models. Look at this graph representing an ordinary differential equation. Instead of introducing it purely as a calculation trick, the curriculum anchors it to a tangible concept, a rate of change. This allows designers to construct perfectly sequenced educational materials. But a perfect curriculum built in a theoretical vacuum rarely survives contact with actual university students. The framework cracks against three limitations. First, subjective experience. Students arrive with different cognitive backgrounds. Second, the classroom social reality. The model isolates math from required communication. Third, pure mathematics lacks empirical tools to measure if students actually learned the material. To patch these fractures, researchers import reference disciplines. They bring in sociological observation and psychological learning strategy questionnaires to evaluate the human variables. But these external patches do not heal the foundational structure. They introduce entirely incompatible materials that threaten to collapse the model entirely. Radford argued educational theories are built on three layers: principles, methodologies, and questions. The top two layers can often cooperate, aligning on a surface level, but the process stalls at the bottom layer, principles, where unstated worldviews about the nature of knowledge prove incompatible. A cognitive framework treats mathematical understanding as an internal state. A sociological framework treats it as an external, communal discourse. They contradict at the root. You cannot mathematically average two contradictory worldviews. To solve the crisis, we need a theory that transcends them. The anthropological theory of the didactic redefines mathematics as an institutional practice called apraxeology. Its foundation is the praxis block, the know-how of tasks and techniques. Above that sits the logos block, the know-why, providing the theoretical discourse justifying why those techniques are valid. This explains the high school to university gap perfectly. A high school curriculum isolates tasks with a very thin logos block. University mathematics demands a massive, rigorous theoretical justification for every move. ATD tracks how mathematical knowledge mutates depending on the institution teaching it. A differential equation in a pure math seminar is validated by abstract proofs, but in this engineering class, the exact same equation is validated by how accurately it models the physical pressure inside an industrial valve. Math is not a universal cognitive absolute. Its very structure is dictated by the institution it lives inside. There is one final step to complete the architecture. We have to map the student's personal experience against the weight of the university. By combining ATD with Halscomp's subject scientific theory, we place the individual's task directly inside a heavy sphere of institutional constraints. This reframes the student struggle. Subjective limitations, like giving up on a proof, are mapped directly to institutional bottlenecks rather than a personal cognitive deficit. By mapping the rigid institution alongside the constrained individual, researchers finally have a unified theory capable of analyzing the true structural causes of STEM dropouts. We can see exactly how these institutional constraints operate by looking at prospective math teachers at the end of their university degrees. Armed with advanced mathematical knowledge, these future educators routinely attempt to design beautifully constructed, inquiry-based lesson plans that focus on deep conceptual understanding. But the sheer weight of institutional pressures, strict curriculum pacing, grading quotas, and standardized testing forces them to abandon those conceptual designs entirely. To survive the system, they revert to the safest possible route. They drill narrow, mechanical calculation routines designed for one purpose: passing the assessment. If educational researchers ignore the heavy institutional reality of mathematics, our most brilliant pedagogical interventions will continue to be crushed by the very systems they are trying to fix.